Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is minimum height trees. So let's go to LeetCode. There you go. A tree is an undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycle is a tree. All right. We already know that. Given a tree of n nodes labeled from 0 to n minus 1 and an array of n minus 1 edges where edges at the ith position represents two value, there is an edge connecting a and b and it's undirected. So basically b is connected to a and a is connected to b. Now in this tree, you can choose any node of the tree as the root. When you select that node x as the root, the result tree has height h. Well, selecting different node as the root will give you different heights, right? So among all possible rooted trees, those with minimum height are so-called minimum height trees. Now what we need to do? We need to return a list of all minimum height trees, root labels, basically that value in an array format. So you can return the answer in any order. The height of a rooted tree in the number of edges on the longest downward path between the root and the leaf. This particular example explains it really well. So let's dive deep into LeetCode 310 minimum height trees. We are given n number of nodes, and then these edges basically represent undirected edges connecting two nodes. So there is an edge going from, let's say here 0 to 1 and then 1 to 0. So in this example, we are given n equals to 4. So we should have nodes from 0 to 3. So 0, 1, 2, and 3. 4 nodes we should see in our graph. So here you can see these different representation of these graphs. And what do they represent? Actually, they represent we choosing different nodes as the root of these tree. Although it's a graph problem, but like graph can be a tree, and if it does not have basically a cycle, and then there is only one edge connecting, there is one edge connecting two nodes basically. So here you can see we have edge 0, 1, 1, 2, and 1, 3. So let's say if I choose 0 as my root, then the height of this tree would be one edge and then going this way. So this is 2. How about this one? This is also 2. Then minimum height of this one would be 2. Minimum height would be 2. So here, if I'm choosing 0 as root, so let's say root equals to 0, then height would be 2. How about if I choose my root 1, then what's the height of the tree? Well, this time, if you try to explore, basically the height is the furthest distance from root to any of the leaf. So here I see that this is 1. This is also 1, this is also 1. So max of all of these heights is, minimum height would be basically that maximum distance from root to all the leaves basically represents the height, and we have to basically return the minimum height trees. So in this case, height would be 1. How about if we choose 2 as my root? So if root is 2, then again I will try to explore all the paths to leave. This is one path till 0. So this here it will be 2, and this one again is 2. So minimum of 2 is, so maximum of 2 is 2. So height would be 2. How about when I choose my root as 3? So this time it will be basically again this 2 and 2. So height would be 2. So out of all of these values, choosing different nodes as my root, then minimum would be this right here. this right here, which is height equals to 1. So that is why our answer for this particular example would be 1, like this. So you return it in an array, because there could be multiple answers. Because let's say if if there was some in this particular example, like that's not possible, but like there was some scenario where height somewhere it was like 3 3 and 2 and 2 and then 4 3, then these two would become basically these minimum height trees. So that's why our answer in that case would be 2 and 2. We will see that, we'll go to that case, but let's see how we are going to find this now. So what we are really doing is we are choosing to do a BFS on different nodes. Isn't that what we are doing? So if you see right here, so a brute force way of finding these minimum height trees would be basically visiting each of these nodes, choosing, or you can say choosing different nodes as the root, and then running BFS or DFS and then finding the height. And I think in this case, a better solution would be BFS, because BFS simultaneously visits all its neighbors, or all the nodes that connecting to the being visited node, and then simultaneously it's like visiting all the nodes at that level. So I think it would be easier for us, or faster, I would say it would be faster for us to get the that maximum path, which will be actually the height of the tree if you're choosing a node as the root. So what we'll be doing is we'll be running BFS. So a brute force approach. So let me write brute force. A brute force approach would be I'm choosing root, for root in range n. So it will run from 0 to n minus 1. So it will choose 0, 1 and 2 and 3 as the roots, and then I will try to find height from BFS. So BFS will be giving me some height for that root. All right, and then I will have some answer variable for me, like some global answer variable. This answer would be basically an empty array in the beginning, and then I will assign this height right here, and then I will actually here I will compare, I will update this answer. So update answer based on update answer with minimum h. All right, so minimum h, and there might be a scenario where this h becomes equals to this h, then actually we will add different h. Okay, so let's say this is not the h, by the way. This is not the h, this is the name of the root. So let's say this returns h, so this root will become the answer. And if this h becomes equals to another h, let's say this h becomes equals to another h, then I will add this root 1 and root 2 as my answer. All right, I hope you're getting what I'm trying to say. So there might be multiple answers for this, but then this brute force approach will not pass on LeetCode, and the reason being, what we are really doing is for all the nodes, so let's say there are n nodes, so for time complexity what's happening is, for n nodes we are running BFS, which itself take, you can say v plus e. Let's say if n is the total number of vertices, v into v plus e. So if you see right here, the time complexity goes up to v square plus ve. Right, so this itself is like not acceptable. It won't pass. So this time complexity will not pass, and that's the reason that I'm calling it a brute force approach, which is really straightforward, very simple. For each node, choosing it as root, find its height. If that height is the minimum, then put that into your answer. If there is already you found some height that was equal to the height that you're currently finding, that add to that node as well to your answer. So that is the brute force approach. But now we will be moving to a better optimize approach. And what is that? Well, that's not very straightforward, but it's all based on some intuition. This problem has been asked by Google, and Google always asks really nice problems. Well, so let's move to a better approach. What is that better approach? So we have to make some key observations. I'm drawing this tree right here. Or graph, you can say. And let's make some observations. What I'm trying to do, I'm trying to find the minimum height of this tree. What is that root? If I choose that root, so that I get the minimum height of the tree. Well, tell me, what are the leaves node that you see right here? Well, this is a leaf node. This is a leaf node. This is a leaf node. This is a leaf node, leaf node, leaf node, leaf node, and leaf node, and leaf node. So I will just mark them as leaf node. Okay, I'll just mark them with L. So these are the leaf node. So LN, 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 salam saab, salam saab. Alright, so these are the leaf nodes that I have right here. Well, let's think about finding the minimum height, choosing these leaf nodes as my root. Do you think that will give me my answer? Let's try. Let's say if I choose this node as my root, so I'll mark it basically, let's say root. Now if I choose this as my root, what would be the height of this tree? So let's try to explore and find the height. So height would be, in this case, this is giving me 4, this is also giving me 4, and this is also giving me 4, So let's say I choose basically this path. I choose this path. So this gives me height equals to 4 when I'm choosing this leaf node. Is that optimal? What is my target? Like, I'm trying to find the minimum height of this tree, and choosing any of these leaf nodes is really giving me like the biggest heights possible. So for this, if I choose this one, this gives me 1, 2, 3, or 1, 2, 3. This one also 3, 1, 2, 3. So this one is giving me 3, height 3, if I'm choosing this as my leaf node. So what's really happening is, it's very logical that if I'm choosing these leaf nodes, of course they're going to give me the height that is maximum possible, because these are the furthest node, these are farthest from the other leaf nodes, right? And that the definition of height is like, try to find the farthest node from this or from this. Even this one will give me 1, 2, 3, 4, still 4. So we are seeing that actually choosing these leaf nodes is not giving me an optimal answer. They are giving me like biggest height possible. So what about if I choose something in the middle? So let's say if I choose this node as my root, then what is the height possible? So for height, it would be, so if I will try to reach the leaf nodes from here. So I will try to reach the leaf nodes from here, this one. So this gives me 2, then this gives me 2. So this gives me 2 here and 2 here. So that is basically height would be 2. So if choosing this one as root, height would be 2. Can you see like more height? Like if, let's say if I try to explore this one, that also gives me 2. So the height here would be 2. So if you see, and that's not just about choosing this one as height. It's all about choosing anything in the middle. Maybe I might want to choose this one as my root, and if I choose that one, so let's say if I choose this one as my root, then what's happening is, again, this one gives me 1, 2, or let's say 1, 2, 3, or 1, 2, 3. Yeah, so this gives me height 3. these are of course better than choosing something on the leaf. So that is why this approach that I'm talking about is pruning the leaves. And while you are pruning the leaves, you are trying to basically get closer to those answer nodes that will give you your minimum height trees. So what I'm really trying to say is, what I want to do is whenever I'm seeing these leaf nodes, I will keep track of these leaf nodes, and I will prune these leaf nodes to get to the nodes that are in the center, because center is what giving me my answers, right? These will never give me my answer, and the reason is these are farthest node from the other leaf nodes. So this one is farthest, at its farthest from this one is farthest from, let's say, this one is farthest from this. So that is why the height of choosing any of the leaf nodes will give me a really big answer. That's not what I want. So my answer would lie something in the middle. So what is that middle? These are the middle nodes. So these are the middle nodes. So my answer would be somewhere here, but all of them cannot be the answer, right? All of them cannot be the answer. So let's say if I take out this part right here, let's say if I'm pruning these nodes, what I'm trying to do is, if I'm pruning these nodes, so I will just paste this right here again and prune these leaves. So I'm just removing these leaves, and removing means getting rid of this, getting rid of this is also leaf, this is leaf, and this is leaf, and this is leaf. So after pruning those, I'm getting somewhere here. So any of these should be my answer now. Any of these should be my answer. But still, if you see right here, that is my answer going to be all of these nodes? Well, no. You can definitely tell that this node right here is actually in the middle of all of the other nodes. So these are also adding 1 height if you were choosing them as root. But if I choose this middle node as my root, then they are all connected at one level with me. So what I'm trying to say is, let's say if this is the remaining graph that I have, or tree that I have, I would want to choose. Now again, I have these leaf nodes, right? This is a leaf node, this is a leaf node, this is a leaf node, and this is also a leaf node, and this is the only center node right now. So let's say if I choose any of these leaf nodes as my answer, let's say if I choose this as my center, as my root, sorry, if this as my root, so what would be the height? Let's say if I choose these leaf nodes, and we've already discussed that we are not trying to choose the leaf nodes because these are the furthest away from the other nodes in that tree. So this gives me the height of 2. Choosing this one gives me the height of 2. So these all leaf nodes give me the height of 2. It's except just this one node right in the center that gives me height equals to 1. Why? Because all the other nodes are connected at just one level away. So this one right here, this one right here, this one right here, this one right here. So that is why again we are going to repeat the same process of pruning the leaves, and we will keep pruning these leaves until my graph contains either 1 or 2 leaves. And I will tell you why there could be either 1 answer or 2 answer, not more than that. I will show you why. So let's say in this case I will prune all these. So prune these. So then what I'm left with is just one root, this node right in the middle, and that is going to be my answer. So our step would be simply, you visit entire graph or create this graph using these edges, create the graph adjacency list. But at the same time, for each of these nodes, maintain some data structure, most likely an array that will keep track of in degrees. That means incoming edges. Why do we need that? So that we can track what are the nodes which are the leaf nodes, because those are the nodes I will be pruning and I will be updating my in degree and graph. So what I'm really trying to say is, all these leaf nodes only have one incoming edge. So that is why I will know what are the leaf nodes so that I can prune them. All right, and then next time I visit, basically I will prune these, I will remove all of these, I will get rid of all their in degrees, and then I will remove them from basically my graph as well. And in the end, I will reach a situation where my graph either has one node or two nodes. All right, so let's look at the example. Where there might be two possible answers. So I'm going to create another graph. Let's say I had this graph, right? I had this graph. So in this graph, tell me, what is our process? Our process is basically choosing these leaf nodes. So this is a leaf node, this is a leaf node. These have just one incoming edge. So I will, on this level, I will prune these nodes. So I'm trying to find the minimum height trees, right? That's what I'm trying to find. So minimum height trees I'm trying to find in this example. So this is a different example. So these will be pruned. What do I left with? I am left with these two nodes. All right, I'm left with these two nodes. Well, tell me which one should I choose as root now? Well, you can choose any. You can choose this one or this one. The height will be same, which is 1. So that is why these both are going to be my answer. These both are going to be in my answer. So let's say if my node were 0, 1, 2, and 3, my answer would be 1 and 2. And the reason is these two, choosing both of these will give me the same height. If I choose this one as my root, then 1, 2 is the height. This is just 1. So height would be 1, and if I choose this one as my root, then height would still be 1. All right, that is why our steps will be basically, it's more like, honestly, it's like a BFS, but it's a smart BFS, because rather than choosing each node, you can now like imagine choosing each node and then running a BFS, right, and then finding the height, and that you're doing it for all the nodes. Rather than that, what we are doing, we are choosing all these leaf nodes, putting them into our queue, put all the leaf nodes into your queue, and then visit their neighbors. So visit this neighbor, this neighbor, and then cut this connection, because you are pruning the leaf. If you cut this connection, and then for this one you'll be visiting this, you'll be cutting this connection, these connection, and then you will later, if you find a node that actually now its in degree is also 1, then you will add it to your leaf, and you will keep doing that. So you are basically moving level by level inside. So this is next level by level inside, such that you get to either the center node or nodes. And there will never be a situation where nobody explains this thing that why there will not be a situation where our answer would be 3 nodes. Why just 2? So let me give you an example why. So let's take this simple example where we have these nodes, these 4 nodes, and in these we have already talked about that choosing any of these 0, 1, 2, and 3, these two are my answers. But what if I add one more node? Let's say, how can we make this like have an answer, 3 node as an answer? So let's say if I add one more node thinking that these 3 could be my answer, well, that's not possible. Why? Because adding one more node makes one side imbalanced. And what that imbalance means is, let's say if I was choosing this as my root, now I would have 2 at this side and 2 this side. So that is why my height would be 2. But previously, remember, 1 was also our answer. But now what we have done is we have created this imbalance right here, which is 3, and this side it's 1. This side it's 1. That is why our answer would be just 2, because we are trying to find the minimum height, and here we have incremented this as just one more. We have imbalanced the side, so that is why it will the height will be basically taking the maximum path to the leaf node. All right, so that is the reason it will not be possible to have three nodes in your answer. Okay, so let's write the time, not the time, I think it's a really long video. Let's write down the code. I think that would be simple. So as I said, we will have our graph. I'll call it graph, which will be a default state of type list, and then I'm going to basically have this in degree, or just call it degree array, initially all 0 into n. All right, now I will be visiting all my edges, so u and v in range, or not range, just let's visit the edges. All right, all the edges. So to my graph I will be adding v to use neighbors, so I'm appending v to use neighbor, and I will be doing vice versa, so that I will add u to v's neighbors, because it's undirected graph. All right, now at the same time, because I'm visiting basically this u, and u has an edge going to v, that means I'm going to increment the degrees for both of these. So degree at u will be, I will say plus equals 1, and I will do the same thing for my degree for v. So degree is basically the connecting edges. So you can call it in degree, that's what we will be dealing with, but since it's undirected, it doesn't really matter, like you can call it degree or in degree. All right, so now I have my graph and degree calculated. What I want to do is I want to calculate this leaves groups. Leaves would be all the nodes that have the degree which is equals to, I would say 1, because that have just one incoming edges from some inner centered nodes, or one of the edges nodes, but they're not leaf nodes. So here we can say I will just have it just empty array. So for I'll say I'll be visiting all my nodes in my in degrees. So for, let's say, node in range, or range, yeah, we can say range n, for I in range n, if degree I is equals to 1, then I will add it to my leaves dot append. I'm appending it to my leaves. Or we can create this as dq as well. So I'll just say dq, yeah, initially empty. All right, so now we will be running BFS. So as I said, so size, initially the size of our graph, size of our graph would be this, and we will keep running our while loop. So see the code. So while this size is greater than 2, let's keep pruning everything. Let's keep pruning. All right, so let's keep pruning. But now I will basically be running, for how many times? So I will be actually visiting all these leaf nodes, which will come from this leaf. But what I'm going to do is I will actually what I really want to do is I want to calculate the size that I will be visiting for these leaves, because I will be adding more leaves so that they can be processed on the next level. All right, so I think a better way would be calculating the size of it. So let's say leaf size, cur size, we can say. That will give me the length of these leaves, and now for this size, for I in range, this size, cur size, I am actually going to pop leaf by leaf. So I'll say leaf would be leaves dot pop left. It will give me one leaf. Now this leaf will have some neighbor, right? Some neighbor, so which I will actually be decrementing its in degrees, and if that node's in degree becomes equals to 1, then I will be adding it to my leaf node. Okay, too much thinking today. So for neighbor in basically in my graph at this leaf, if this leaf, what I'll do is I will decrement its in degree. So I will decrement its in degree. So in degree for this neighbor minus equals to 1, and if degree of this neighbor becomes equals to 1, then it's a leaf node, and if it is a leaf node, I will append it to my leaves dot append this neighbor. All right, but here we were calculating the size of the graph, and for this leaf node, what I want to do is I want to actually remove it from my graph. So this leaf, I can now, once I'm done processing all its neighbors, I can remove this leaf from my graph. So I can say delete. I think there is a way how to delete a key. Delete a key from Python graph. I forgot, I haven't done it lately. Yes, this is the way. It's okay, we can search, we're not expert of Python, we are expert of solving the problems. So here for this graph, I will just send in the leaf. So I'm removing that, and then finally I will have basically I'm calculating this size, but this size is actually out of the graph. So we need to keep updating this size, right? So after this is done, you deleted that, then I will update this size again, right? It's a variable, so that I get new size now. All right. So finally I will have basically my graph either with one value or two values. So I will create my answer. So answer would be this empty array in the beginning, and now for key val in graph dot items answer dot append key, and then I will just return this answer. Return this answer. Yeah, you can see I'm not very fluent writing this because I have not solved this earlier, but I hope the logic was right. So let's try to run this and see if we made any typos. Oh my god, no way. No, yes, okay, I'm getting it. So if n is equals to 1, then I will be return basically 0. Return 0, because the height of, if the n is 1, then the height would be just 0. That's the edge case I had in mind, but I didn't write it. Boom, let's go. I'm so proud of myself. It wasn't easy. It was just all in my head, and now it's next to us. We can see the entire code. Yes, we can. Let me zoom out. Oh my god. Awesome. Let's write down the time complexity now. At max, what we are doing, we are visiting just all the nodes. That's it. Earlier in the brute force, the time complexity would have been n square, but for this one it's going to be big of p plus e, because we are visiting all the nodes at max just once, right? And then for space complexity, it's going to be also be an e, because we are storing our graph into this adjacency list or dictionary, you can say. For space complexity, also going to be v plus e. So I think most of the solutions of graphs should be wrapped up into the time complexity of v and e. If not, just treat it as like some brute force solution, and then get to the your optimized solution. All right, let's mark this problem solved. See you guys later in the next problem.